This screencast is on how to deal with equilibrium problems when you have a mixture of weak acids. We're going to use the same method as we did with weak acid calculations. We still focus on the major species. And so we're going to be going to sample problem number 3 on your worksheet that's titled Acid-Base pH Calculations, Guided Practice and Independent Practice. So for the moment, I'm going to switch screens here and go to that worksheet. All of you got that in class. So what we have here is a problem that says calculate the pH of a solution containing 1 molar of HCN and 5 molar of HNO2. It also wants us in the end to calculate the cyanide ion concentration at equilibrium. So what I'm going to do here is I'm going to attempt to draw a little picture here to help us picture what's going on. So if this is your beaker, your system that has these acids in it, if it's an aqueous system, of course we know that it has water in it, okay? And so water auto-ionizes itself, forming the hydronium ion and the hydroxide ion. So that's always going on there. And remember, the Kw for water, which is its equilibrium constant, is 1 times 10 to the negative 14 at room temperature. And unless they tell you otherwise, you assume these are at room temperature. Let's see if I can change my pen color here. So the other acids in here, it tells us, are HNO2. And that Ka value is 4.5 times 10 to the negative 4. That is a 4. Looks like a 9. Let me try to fix that. And so the equilibrium, since this is a weak acid, it will dissociate into the hydrogen ion and the nitrite ion. And then the other acid in this container is HCN. It will dissociate into the hydrogen ion and the cyanide ion. The Ka value for that is also given, for that acid, is 4.5 times 10 to the, let's see, I'm reading the wrong thing. The Ka value for that is 6.2 times 10 to the negative 10. All 3 of these acids are producing hydrogen ions in solution. So one thing I want y'all to understand is once they're all in the same container, the hydrogen ions basically are all the same. You consider them the same. So the thing that controls the pH, which is one thing they want us to calculate, is the strongest acid. Controls the pH. So how do we tell which is the strongest acid? That's right, we look at the K value. So the K value that is the greatest is going to indicate the strongest acid. So the greatest K value that we have here is HNO2. This is the strongest acid present in this mixture. So it controls the pH. So we're going to calculate the pH based on this equilibrium that forms. So we're going to ice the problem. HNO2 is in equilibrium with H plus NO2 minus. So let's come in and we're going to set up our problem here and we're going to ice the problem. So ICE. And initially you are told, as far as the HNO2 goes, that we have a total of 5 molar. Zero and 0 for the 2 ions initially. Since this is a weak acid, we define our shift in terms of x. So minus x plus x plus x. Remember, if you have an initial amount present, you can neglect your x. So at equilibrium, we have 5.00 molar of the nitrous acid. We have X and X of the two ions. So we're going to set up our law of mass action. Which will be hydrogen ion concentration times the nitrite ion concentration divided by HNO2. So let's substitute in our values. So we know the Ka of HNO2 was 4.5 times 10 to the negative 4. And that's going to be equal to x squared. And this is an approximation. Remember, we can neglect x here. So we're approximating that that's equal to x squared over 5.00. So we're going to cross multiply here, and then we will, let me scroll up some. We're going to cross multiply here, and then we will take the square root of x, and I'm going to go ahead and do all of that at one time. So cross multiplying and taking the square root, that gives me my x equals 4.7 times 10 to the negative 2 molar. And remember from our chart, X is the hydrogen ion in this case. So we just found the hydrogen ion concentration in this mixture of acids. So that means the pH is equal to the negative log of 4.7 times 10 to the negative 2. And so the pH is equal to 1.32. Remember, the number of sig figs in your concentration is equal to the number of decimal places in your log. That's the rule for sig figs with logs. So we just found the pH of the solution, which is one thing they ask us to calculate. So we've just done this. And the next thing it wanted us to find was to calculate the cyanide ion concentration at equilibrium as well. So I'm going to just sort of come over here and take care of that part of the problem over underneath. So to find the cyanide ion, you want to be working with the dissociation of the hydrogen cyanide. Now, keep in mind what I said earlier, that once they're in solution, all the hydrogens are considered to be identical. So we already know the hydrogen ion concentration is 4.7 times 10 to the negative 2 at equilibrium because we just found that. We just found that that's what that was equal to, 4.7 times 10 to the negative 2. Remember, initially, the HCN is given to us in the problem as being 1 molar. We would normally go 0, 0 initially, minus x, and plus x. And like I said, we just found x. We can neglect the x here, 1.0. And since we know the hydrogen ion concentration, we know the HCN when we're neglecting x, and we know the K value, we can use the law of mass action for the reaction here, which is going to give us the Ka was 6.2 times 10 to the negative 10 is equal to concentration of hydrogen, 4.7 times 10 to the negative 2 times x divided by 1.00. I'll let y'all kind of let that soak in a little bit. And I seem to have, let's make my calculator trying to locate that. If you do go back and check the 5% rule on this one, class, you will find that the x is less than 5%. So we got 6.2 times 10 to the negative 10 times 1, and then divide that by 4.7 times 10 to the negative 2, and that's going to be your x. So x equals 1.3 times 10 to the negative 8 molar, and that is your cyanide ion concentration.